Hi, I'm Avi Friedlander, a PhD student at Queen's University, and I will be presenting work that I've been doing along with Katie Mack, Sarah Shun, Ningcheng Song, and my supervisor, Aaron Vincent. I'm going to start off this talk by discussing primordial black holes in general. I'm then going to spend a little bit of time discussing theories of large extra dimensions. The meat of this talk will be discussing ways that we can observe these extra dimensional black holes, and I'm going to finish with some concluding remarks. So, primordial black holes just refers to black holes that were created some way in the very early universe. These black holes, after they form, they evaporate via Hawking radiation, and if they survive until today, they serve as a very interesting cold dark matter candidate. Because of this, they've been studied extensively in 4 dimensions. However, as I will show in this talk, extra-dimensional black holes behave quite differently and therefore deserve their own attention. So when I talk about extra dimensions, I'm talking about theories such as the ADD model, which proposes that the true scale of quantum gravity is much lower, closer to the electroweak scale. It does this by proposing we have some additional extra dimensions that are compactified to some submillimeter size. On scales smaller than that size, the gravitational potential drops off much quicker, and not like the 1/r potential that we expect. On scales larger than the extra dimensions, we regain the regular 1/r scaling we expect in Newtonian gravity. This allows us to solve the hierarchy problem while still maintaining all of our large-scale gravitational observations. There's a couple important consequences for black holes, because black holes are governed by our theory of gravity, and we are changing our theory of gravity. Quite notably, the black holes will have a larger Schwarzschild radius, and will have therefore a smaller Hawking temperature. You can see this plot of the Hawking temperature as a function of the black hole mass. This dark blue line is the regular 4-dimensional case, and these other lines are for different numbers of extra dimensions from 2 through 6. And you can see in all of these cases for the light black holes, the black holes will be less hot than the 4-dimensional case. Another really important consequence is because particle collisions with energies higher than the scale of quantum gravity produce black holes, the lower scale of quantum gravity provides a very simple way to produce microscopic black holes in the very early universe. Additionally, because the Schwarzschild radius is larger, these microscopic black holes will accrete, whereas 4-dimensional black holes will not. This provides a new production mechanism for producing primordial black holes that doesn't rely on any details about inflation. So after the black holes form, there's 2 main processes that will affect the mass. You have evaporation and you have accretion. And typically one of these processes will happen at a time. So first, looking at the first process, which is accretion, a microscopic black hole forms, and if the universe is hot enough and therefore dense enough, the black holes will grow. So here you can see the x-axis is the reheating temperature where the black holes form, and the y-axis is the black hole mass. And as long as the black holes are on the right-hand side of this threshold, hotter, the universe is hotter than some threshold, the black holes will grow into some asymptotic mass that's much larger than the scale of quantum gravity. And then after the black holes accrete and grow to some mass and the universe cools down, the dominant process is evaporation. The black holes will lose mass to Hawking radiation, and the amount that it loses depends on the number of extra dimensions and the mass of the black holes. And you can get a wide range of lifetimes of the black holes, so you can have black holes that evaporated any time between Big Bang Nucleosynthesis, all the way to black holes that are still around and will be around for a very long time. When I talk about Hawking radiation, it's important to note that this Hawking radiation will produce all particles that have masses lower than the Hawking temperature. And it will produce these particles with a spectrum that is nearly thermal. Here we have a black body spectrum with some sigma I, which is a gray body factor that distorts the spectrum, which we calculate. Additionally, if you're producing massive unstable particles, they will decay and create cascades of secondary photons and electrons, which we determine using the PPPC for DMID tables. Because these black holes will be evaporating from the time they form until they're gone, there are many different astrophysical signals that they can have an impact on. In our studies, we are looking at Big Bang Nucleosynthesis, the galactic center, isotropic photons, the CMB 21 centimeter cosmology. But for the purpose of this talk, I'm going to just focus on these first three. So Big Bang nucleosynthesis is when the universe first cools down to about an MeV, and light nuclei such as helium and lithium can form. If we introduce primordial black holes into cosmology, it can have a big impact on BBN. Notably, if you have a lot of black holes or evaporation products, this can change the expansion rate, therefore changing when neutrons freeze out, and which will also have an impact on how much helium you end up with. Additionally, if you have the black holes evaporating during BBN or after BBN, and producing high energy hadrons or photons, these evaporation products can dissociate helium, reducing the amount of helium you form and turning it into an increased deuterium abundance. So, to actually calculate the exact impact on the abundance of the light nuclei is a very complicated process that you have to take into account a very large nuclear network. So this has been done in detail for the case of decaying dark matter, which has a lot of similarities to primordial black holes. So our analysis of primordial black holes during BBN is drawing off recent work, which recast decaying dark matter onto the constraints for four-dimensional primordial black holes. We are adapting that work and extending it to the case of large extra dimensions. So when I talk about recasting, the decaying dark matter particles have two main properties. You have the lifetime of the particle and the mass of the particle. These two properties can be cast onto mass of the black holes by ensuring that the average time that energy is injected into the universe, and that the average energy of each particle is the same between the primordial black hole case and a corresponding decaying dark matter model. Additionally, the constraints are set in terms of some entropy units in the decaying dark matter case, and that can easily be recast into the fraction of dark matter that is comprised of black holes in the early universe. Using this recasting, we have some preliminary constraints on the abundance of black holes in the early universe in the case of 3, 4, 5, and 6 extra dimensions, as you can see here. Next, looking at black holes that survive all the way until today and beyond, those black holes will be very abundant in the center of the galaxy, where there's a lot of dark matter. These black holes will be evaporating into photons, and those photons can be observed in an experiment such as integral. So we calculate the expected flux from these black holes by integrating different lines of sight through the galaxy. You can see here in this diagram, here we're the sun, and we can do different lines of sight through the galactic center. And depending on the abundance of dark matter along those lines of sight, calculating this D integral, you will get different fluxes. And we compare these expected fluxes to pre-processed 6-year integral data that is pre-processed so that we have likelihood functions that's binned by energy and latitude. Additionally, if the black holes survive until today and are still hot enough to be producing positrons, those positrons will annihilate into a 511 keV line. So we can calculate the flux directly to that line. This is a very similar calculation. We have that same d integral, but now it depends on the amount of positrons we're producing. And this can be compared to integral 511 keV line, and we use a more recent data set for this. And using these two sources, we can get some preliminary constraints. Here, the x-axis is the mass of the black hole. The y-axis is the fraction of dark matter that was initially made up of these black holes. And here you can see the constraints. The solid line is from evaporation to photons, and the dashed line is evaporation to positrons. Depending on the mass of the black hole today, and therefore the temperature of the black hole today, at different points the photon evaporation or the positron evaporation is dominant, so you do have to include both of these processes. Additionally, that's a very angle-dependent signal, but we can also have strong constraints from isotropic photons. A main source of isotropic photons is an extragalactic background light. Black holes outside of our galaxy will evaporate between recombination and today, producing photons that can be observed in telescopes at Earth. So we track the photon spectrum from recombination and updated it at each discretized redshift step using this equation that looks a little complicated, but there's three things going on. Photons can lose energy, they can be observed and therefore attenuated. At each redshift step, we add photons from recently evaporating black holes. The energy loss mechanisms that we include is redshifting from the universe expanding. Photons can Compton scatter off electrons, depositing some fraction of energy. Then we have attenuation from photons being absorbed by neutral hydrogen, ionizing its electron, or photons, high energy photons, pair-producing electron-positron pairs. It's important to note that all of these scattering processes are only important for when the universe was very dense, so at redshifts greater than 100, for the energy range that we are looking at. And below redshifts of about 100, only redshifting is the important process. And when we look at adding new photons at each redshift step, there are three main sources. Looking at this one example of a black hole mass, we have the direct evaporation to photons. We have this neo-gray body spectrum that I talked about before. Black holes that are hot enough to produce positrons will have those positrons annihilate via positronium, as seen in this orange line. And also, if you're producing electrons and positrons and they are energetic enough, they will upscatter CMB photons, and you get this tail of inverse Compton scattering photons. So beyond the extragalactic black holes within the galaxy will also contribute to the isotropic signal. As I discussed before, the galactic signal is very angle dependent. However, it will contribute a non-zero signal in all directions. So by calculating the flux in the direction directly away from the galactic center, we get some minimum flux from the galaxy that we will see in all directions, and therefore it will be indistinguishable from an extragalactic isotropic signal. By combining the galactic and extragalactic isotropic signals, we can get a theoretical flux and compare it to a large range of X-ray and gamma-ray telescopes. And by ensuring that the theoretical flux is no larger than the observed flux at any point, we can get these preliminary constraints, where we can constrain how much dark matter we have for different numbers of extra dimensions from this isotropic signal. The main takeaways I want you to have from this talk is that theories of large extra dimensions generically predict the existence of primordial black holes. The astrophysical effects of these extra-dimensional black holes are very different from regular four-dimensional black holes, and therefore constraints from things like BBN and galactic center and isotropic photons change quite a bit and have to be recalculated for extra-dimensional black holes. thank you very much for watching my talk. If you have any questions, please feel free to contact me at my email.